Okay, so I'll get started and people can join as they want to. So I welcome you all to the problem solving and live interaction session for the subject engineering mechanics. And today we will be discussing the contents of week 10, some problems from week 10, that is rotating frame of reference and something to do with Coriolis force. Coriolis acceleration, not Coriolis force per se, because right now we are dealing with kinematics alone. Okay, so we'll move to the first problem. So it says while a swing bridge shown in the figure is closing with a constant angular velocity of 0.8 radians per second. So it is given that it is constant and it is closing. So omega, if we see in vector form, it is nothing but we are able to see that the axis is pointing towards positive z. So it is 0.8 k cap. So while this is happening, a man runs along the roadway at a constant speed of 2 meters per second relative to the roadway. So we are able to see the person here in case it's not visible. So he is running away from the is running away from our fictitious origin, so to speak, with a constant speed of 2 meters per second, and this is measured relative to the roadway because a person, any gadget or any person who is placed on that roadway is what is measuring this. So it is a relative velocity. So determine the magnitude of absolute acceleration at this instant when d is equal to 6 meters. So d is nothing but from our fictitious origin, the distance of this man is what is d is 6 meters. So let us try to solve this. So some quantities have been given. So we know that omega is 0.8 k cap, and the position of the person with respect to the origin at this instant is origin of person with respect to the origin at this moment is we are able to see it is in the negative y direction at distance of 6 meters. So it is nothing but minus 6 j cap. Okay, and then what else is given? That is the person is running away at a relative velocity of 2 meters per second. So v relative magnitude is given to be 2 meters per second, and we know the direction as it is given is running around. So vrel vector is nothing but the magnitude is 2, so it is minus 2 j cap, and this is constant is what is given. So essentially ARL is 0. Likewise for the RFR, alpha is 0 because it is given that it is rotating with a constant angular speed of 0.8 k cap. So acceleration of the person is what is asked. So from rotating frame of reference analysis, we can see that acceleration of the person, absolute acceleration of the person is again same a naught plus omega r plus alpha r plus we'll have the Coriolis component plus ARL. We'll have this big expression. But many terms here go to 0. This is the axis about which it is spinning, so no acceleration here. It is spinning with a constant velocity, constant angular speed, and our ARL also is given to be 0. So AP we can calculate it as 0.8 k cross R is minus 6 j cap plus 1.6 k cross VREL is minus 2j, and that's about it. So acceleration of P is, this will give a minus I minus 2 into 1.6 I, and this will be minus 0.8 squared into minus 6 j. So acceleration of P is 3.2 I. K plus A is minus I. Yeah. And this will be 0.8 squared into minus 6 minus of this is 3.84 J. So magnitude we can calculate easily. It is comes to 4.99, that is 5 meters per second squared. So absolute acceleration is magnitude is 5 meters per second squared. So are there any questions here? And one point to note, in the last session when we were solving for the acceleration in one of the problems, I think the value somewhere in the cross products got missed out. The absolute acceleration would come out to be around 3.04 something, but it in the calculation it came out as 2.6. So I have corrected that in the sheet. I will be uploading that sheet very soon, and the video also, just a small clip for that portion, so that people who refer to it later don't have a confusion on that part. I have re-recorded. I'll put all this together and we'll be uploading it soon. So that is one clarification I just wanted to make. So other than that, if there are any questions in this problem, we can take it now. Otherwise, I'll move on to the next problem. Excuse me. Okay, so I take it that it is clear. So let's look at the next problem. Okay. So person B fires a bottle rocket towards A while sitting on a horizontal disk of radius 2 meters. So horizontal disk meaning we are looking at this view which we are seeing is from the top. This is in the horizontal plane. So its rotation is in the horizontal plane. Radius is 2. So radius of this disk is 2 meters, rotating with a constant angular velocity of 3 meters per second. So omega of the disk is clockwise. So it is 3 meters per second, 3 radians per second. I'm sorry. Okay, magnitude. At the instant shown. At this instant, the speed of the bottle rocket relative to the disk is 1.2 meters per second. So we are able to see this is the representation for the bottle rocket. So at that instant, it is moving towards A with a relative speed of 1.2 meters per second. That is relative to the disk, which itself is rotating, and is speeding up at 18 meters per second because there is something igniting. The gunpowder is igniting in the rockets. It is making it speed up at a at an acceleration of 18 meters per second, and that acceleration is measured relative to the ground. So answer the following questions at the instant based on the given data. Okay. So which one of the following options of these two represents a rotating frame of reference which would result in easy calculation of kinematical quantities as observed by person A, is what is asked. So since there are two, so you can just take a poll. I mean, you can just consider typing in the answer and the chat box if that is the case. Which one do you think would result in easy kinematical quantity? See, the basic idea is that when we are dealing with rotating frames of reference, all the relative quantities start coming in, VREL, AREL. All these are with the disk. Yeah, so all these are with the disk. So when we have pinpointed that this is a person has to measure the relative quantities, so it is better that we make the person the origin and observe the things. So yeah, exactly. So both of you got it right. So essentially, we will be fixing the rotating frame of reference at A and then observe things. as while rotating along with the disk, so that we will be able to see what we are looking for. Okay, so yeah, so let us move on to the next this thing. So now we have a disk and we have fixed the rotating frame of reference like this. So naturally, z points outwards. So our omega, by that convention, omega of the disk, which is the RFR, is nothing but positive, and the value is given to be 3. So it is plus 3k cap. Okay. So and we know that our bottle rocket, let me use another color for that. So this is the bottle rocket which was fired. So it was having V relative in this direction when it was fired, at the instant it was fired. And it is having A, but that is the absolute acceleration that is seen from the ground, is what is given. Okay, so which of the following numbered vectors correctly represents, right, let us see. So which of the following numbered vectors correctly represents the Coriolis acceleration of the rocket? So Coriolis acceleration we know is 2 omega cross VREL. Okay, so omega is pointing outward, and VREL we have it as minus I. So k cross minus I, it is nothing but minus j, because k cross I is j, so it is minus j. Yeah, exactly. So both of you have got it right. So it is nothing but actually it is j cap. Uh, how this comes about is k cross minus I equal to minus j cap. All right. So magnitude is asked. So we know that this is, we can just substitute the values, k cap cross VREL. VREL was given to be here. VREL is given to be 1.2 meters per second. So we have it as 1.2. This will be I, minus I. We just saw the unit vectors play there. So 6 into 1.2. So we have 7.2. So Coriolis acceleration is minus 7.2 j cap. Okay. So next what is asked is, what is the magnitude of the acceleration of the rocket in meters per second as observed by person A, who is sitting and rotating with the disk? So naturally ARL is what is asked. So if we were to just calculate this, we know that acceleration of the rocket, absolute acceleration of the rocket is given to be 18, and it is said that it is speeding up. So it is having a velocity this way, and if it is speeding up, naturally the acceleration has to point. Yes, Sudhakar. No, once it is released, it is in space. It is not in contact with anything. Yeah, yeah. So, so we have this as 18 meters per second squared is what is given. So from our vectors, we can see that acceleration of the rocket would actually be minus 18 I cap. This is measured relative to the ground, which is the absolute acceleration. So we have a recipe for absolute acceleration. What is it? It is acceleration. Acceleration. Let us consider the actually the object, the rocket at this instant is at point B. So we can take it to be acceleration of that point B plus omega of the RFR, which is the disk, cross omega disk cross R of B with respect to our O, plus alpha of the disk. It is better to write all the quantities first and then turn to which go to 0, so that we don't miss out on anything. This is RB with respect to O, plus Coriolis acceleration that we have already computed. So I'll just omit writing 2 omega cross VREL. And then AREL is what is asked. So we can see that this term goes to 0. Okay. I'm sorry. We are observing it from A. So we have to take the acceleration of A here, here, acceleration of A plus, then we are observing that point B. Point B could be the person B or the rocket B because both are at this instant are at the same point. Okay, so this is 0 and our omega is 0 because it is rotating with alpha is 0 because it is rotating with a constant speed. All right. So AR we know it is minus I cap. So omega of the disk we know it is 3 k cap cross 3 k cross R of B with respect to, there is another point to be noted. It is not O, it is A. I'm sorry about that. Please take note of this. Here also it will be A. All right. So RB with respect to A is nothing but the radius. So it is radius was given to be 2 meters. So it is 2I. Okay. So we have accounted for the centripetal. Then alpha cross R is 0. Then Coriolis acceleration, we just got it as minus 7.2 J cap plus ARL. Let it be ARL for the time being. So if we were to calculate this, we get 3918 k minus 18. Yeah, naturally the values are given such that they cancel out, plus ARL. So these cancel out. So our relative acceleration is nothing but our negative of the uh, it is nothing but 7.2 J cap is what we are, is what person A observes. So this is what is asked. So the magnitude or the relative acceleration is magnitude of ARL, which comes out to 7.2 meters per second squared. Yeah, yes, please. No, no, A is not fixed. See, your question is right, but the question qualifies that A is rotating with the disk. Okay, so that's fine. A has zero, so A is not having any velocity or acceleration. Uh, uh, no, rocket is not touching the disk, but no, essentially, the what is the essence of saying that person is sitting at A and rotating with the disk and observing? From that vantage point, what will be the relative to this disk? What will be the acceleration? Is what we are trying to ask. Now you may argue that person has some dimensions and then it cannot be idealized as a particle. That, but it is rotating, no? But point no, but the line of sight would differ, right? Yeah, it's not in the same line. It is perpendicular to the VREL actually. It is in J cap, so it is perpendicular to the actual relative velocity. Why that is happening is because the person is rotating. Okay, no, I'll try to substantiate. See, the idea behind asking this is a disk is rotating. Now, when such things happen, what will be the relative acceleration with respect to some point in the disk? How we can substantiate that easily is by placing a person there, observer there. Observer may not have a velocity, that's fine. But if the person is fixed to that frame, there is no relative motion between the person and the frame. So naturally, the person has to follow the same motion as the disk. Yeah, yeah. Disk is rotating, no? Why is the disk not moving? Yes, absolutely not. But there is rotation, right? No. Okay. No. What you are arguing is that I'm talking about the line of sight. If I were to draw, no, at this instant, I connect point A and B. I have a line along which only VREL is measured at this instant. No, no. See, the person doesn't realize that he's rotating. That is the whole crux of it. Okay, so the person, if the person were to take cognizance of that fact, then it was easy to measure Coriolis force also while rotating. That is not the case. We cannot measure it. That is why we compensate for it mathematically. Not slower. Why slower? No, it is not towards the velocity. No, our acceleration is perpendicular to the velocity. If you see, VREL is pointing towards the person A, whereas acceleration, the relative acceleration that is measured has a J component only, not I. So if you were to let this be, then the person would actually see a deviated path. Okay. Yeah. Okay then. So let us move to the next problem. Okay, that is also a little bit related only. Persons B and C each throw balls as shown while sitting on a disk rotating in the horizontal plane with a constant angular velocity as shown. Okay. So consider the balls to have no acceleration, no horizontal acceleration. Once it is released, there is no horizontal acceleration. So, which of the following option correctly depicts the possible paths of the balls as observed by persons B and C who are rotating with the disk? So actually, this person throws a ball that way, and this person throws a ball or object, whatever it is, that way. So as time passes, as they rotate in this sense, what is the possible path that they will observe of the object that they threw? What is the possible path that they will observe? So here are the four options. So you can just take a shot at it. It is very much related to what we just discussed. So there we had some acceleration. We had to absolute acceleration. We had to compensate for that. Here it has been directly given that there is no horizontal acceleration. So essentially, our key comes as this only. This is the key. So relative acceleration is nothing but negative of the Coriolis acceleration. So you can just take a shot at it. You can just perhaps type it in the comment box itself, and then okay. So we have one answer. Okay, let me explain. So you have figured it all right. So essentially, what we are saying is when there is no horizontal acceleration, our A relative is nothing but our negative of the Coriolis acceleration. Okay, Coriolis acceleration we know is omega cross VREL. So the path that the object will take will be in the opposite direction to what will be dictated by the Coriolis acceleration. So we can see that our angular velocity uh, Coriolis is 2 omega cross VREL. This is pointing out of the plane of the paper. Whether it is positive, negative, that will be defined by our coordinate axis. That is fine. But it is essentially pointing out of the plane of the paper. So if you were to take this case first, let me take this case first. So this is pointing out of the plane of the paper, and I have my VREL that way. So my Coriolis acceleration is acting. My Coriolis acceleration comes out to be this way. So what will I observe relative to the when I am rotating? What will I observe will be opposite of this. So essentially, my path which I would be taking would be towards the path which I would observe would be towards the right when I'm rotating that way. So we can see that the person C would observe something like that. Okay, now let us come to, so that rules out C and A. Okay, and likewise, if we were to see omega cross VREL, so our Coriolis acceleration acts like that. Direction of the Coriolis acceleration is that way. So our path that the person B would observe would be negative of this Coriolis, which will be towards that. So we can see that our option B is what matches this. So, which is why this is the correct paths that would be observed by these people rotating with it. So, if there are any questions, I'm happy to answer them. Okay, so I take it that this is clear. Yeah. The omega is pointing out of the plane of the paper, out of the plane of our screen. So VREL is this way. So what is the Coriolis omega cross R, no? Omega cross VREL. Our Coriolis acceleration is that way. So what we will observe while rotating would be opposite of this. So it will be towards the right. So that is why it deviates towards the right. Same applies for B. Same applies for any point, as a matter of fact, just that it has been shown with 3 points. So Coriolis, exactly, exactly. So what was asked is, what will they observe? Given that there is no horizontal acceleration, what will they observe? It will be, equation suggests that it will be nothing but negative of the Coriolis acceleration. Yeah. Okay. So let us move on to this problem. So we have a circular slotted disk. So circular slotted disk meaning there is a circular disk and then it has a slot which is a circular arc. Okay. So this slotted disk has the circular arc has its center at O. So the radius of that circular arc is 1.1 meters from the figure itself. So this circular slotted disk rolls on the ground without slipping with an angular velocity and angular acceleration of omega equal to 5 and alpha equal to 2.5 as shown. So it is given that both are clockwise. So in this question we've already fixed it xy. That's fine. So our omega of the disk is minus 5 k cap and our alpha of the disk is minus 2.5 k cap. It is known that pin P, there is a pin in this slotted in this slot, is moving from point A to B at a constant speed of 1.5 meters measured relative to the disk along the circular slot centered at O. So that is what I said upfront, that its center is O, center of the circular arc is O, and this is having a velocity, rather a speed. So magnitude of VREL is given to be 1.5 meters per second. Its vector will be defined by at which point we are seeing it at. And it is given that the speed is constant. So it will be tempting to say that ARL is 0. So we should take in the fact that it is moving along a circular path. So that is the key here. So we will see that. Ignoring any gravitational effects, answer the following question at the instant depicted. The magnitude of absolute velocity of P of that pin is what is asked. So we can, let us fix it here. It's fine. XY. So let us work this out. What will this be? Velocity of pin P is, velocity of center is labeled O plus omega cross RP with respect to O plus VREL. This is the addition when we are rotating. Now velocity of O itself we can find because it is rolling without slipping. So it is nothing but velocity of O magnitude, or rather even I can minus 5k cross 1.5j. So this will come to 7.5 I, moving towards the right. Okay. So this is 7.5 I cap. So velocity of P, we can take it to be 7.5 I plus disk is rotating with 5 minus 5k cap. Now sitting at O, if we observe P, we can see that P is exactly at the along the it crosses the y-axis at this instant is what is the essence here. So our position vector RP with respect to O is nothing but 1.1 j cap, and we have been given that it is moving along that circular slot with a constant speed. So VREL, absolute velocity, absolute value, that magnitude of VREL is it is given to be 1.5, and at this instant VREL will be that way, perpendicular. So which is coinciding with X. So it is nothing but 1.5 I. So our velocity of P is 7.5 plus 1.5 plus K cross J is minus I. So it will be 5 into 1.1 all I. This is 7.5 plus 1.5 comes to 14.5 I cap. So magnitude is asked. So it is just a single value. It is 14.5 I cap. Okay. So the magnitude of Coriolis acceleration of P is, you can see it is 2 omega cross VREL, which is 2 into 5K crossed with VREL. We found VREL to be, here we saw it was 1.5 I. So K cross I is J, 10, 15 J. K cross I, K cross I is J. Yeah. All right. So the magnitude of absolute acceleration of pin P is asked next. So that is a little big expression. So let me just add a page here. So our acceleration of P is nothing but acceleration of O plus omega alpha cross R Coriolis plus A relative. Okay, so here acceleration of O, we know it's a linear acceleration for the center of the disk. It is nothing but alpha R. Alpha is 2.5 minus 2.5. When you cross it, it will give a positive quantity. So 2.5 into 1.5, it is 3.75 I plus omega cross R we already calculated here, but nonetheless let us do it again, that's fine. Minus alpha is minus 2.5 plus Coriolis we found was 15J plus AREL. So AREL, we should take note that it is not 0. Uh, Tangential AREL is 0. If we had a straight slot and it was moving at a constant speed, then AREL is 0. But it's a curved slot. It's a circular slot, so there will be centripetal acceleration invariably acting. So our AREL is nothing but our V squared R, which is pointing this way at this moment. So this will be AREL, which is V squared. V is VREL squared by magnitude of R P with respect to O, which is 1.5 squared by our 1.1, pointing J minus. So this is our AREL. So it is 1.5 squared by 1.1, 2.045. Any questions? Okay, thanks. So we have here minus It comes to 45 by 22, 2.045 J. Okay, so rest is just straightforward addition, 3.75. This will give J. K cross J is minus I, so it will be plus 2.5 into 1.1. Rest is everything is J. I plus minus of minus 5 squared into 1.1. This is J. Then plus 15.045 J. So acceleration of P is 3.75 by 2. 6.5 I. Okay. So this is the acceleration we are getting. I hope the calculations are fine. Anyway, conceptually, we have to appreciate it. Calculations you can verify on your own. So the magnitude, we can take it to be 6.5 squared plus comes to 15.94. Okay, so this 3.75, 5, 1.1, 15. Yeah, yeah, I think the calculations are fine. So this comes, acceleration of P comes to 15, what was it? 15.94. This is our answer. So I encourage you to solve it along. In case there are any calculation errors, please point them out. But anyway, I will be checking these again before I upload the Google Sheet. So, all right. So, are there any questions regarding this question? Are there anything that needs clarification? Okay, I take it that it is clear. So, we'll move on to the last problem here. So, we have two links. One has a pin which goes over a slider which is sliding over the other link. So, we have link OQ and link RS. OQ and RS are connected using a pin and slider mechanism as shown. At some instant when theta equal to 75, theta is this is theta, this is 75. The magnitudes of omega of this for this link, the angular quantity magnitudes are given. Magnitudes are given in the direction shown. So it is given to be clockwise both. Answer the following question with respect to the positive xy. So with respect to that coordinate system, we have to report our answers. Okay. So let us see. X cross y, again k points out of the plane of the paper. So we can see that omega of OQ is minus 10 k. Alpha OQ is minus 3.5 k. Okay. So, all right. Let us look at the first question. It says if RP with respect to O represents the position vector of pin P relative to O. So this is the vector we are talking about. This we have to express in X and Y. So this we know it is perpendicular. we have a line. Y-axis perpendicular. So if I were to move it here and extend, I know that this is 90 degrees. Okay. And further, if I were to complete this and this, I have two triangles where this is 0.6 theta. In case you didn't see it there, I'll just erase it. It gives 0.6 theta. So when theta equal to 75 degrees, 0.6 is 45. So this is 45 degrees. This is 75. So this angle is nothing but our 60 degrees. Now in this triangle, if this is 60, this is 90, then we can see that this is 30 degrees. Okay. So we know that RP with respect to O magnitude is 1.5 meters. So we can resolve this into x and y components. X is this, y is this. So y is essentially negative in the negative direction because our position vector would be like that, the component. So if we were to write this, it will be nothing but x component would be 1.5 sine 30 degrees. And this is along the positive x-axis as given. So it is 0.75. Y component. Y component, we can see this is our y component. This is our y component. It is pointing in the negative y direction. So it is nothing but minus 1.5 cos 30 minus 1.29 or 1.299. So it is 1.3. So R in the xy coordinate is 0.75 I minus 1.3 J. This is relative to the coordinate system that is attached to the link RS as given. Okay, so far so good. Again, the absolute velocity of pin P is asked. So we know that absolute velocity of pin P, because this pin is connected to this link. It is connected to that link. So velocity of pin P is velocity of O plus omega O, I think it was called OQ, yes, OQ cross R P with respect to O. Yeah. So this we know to be 0. So velocity of pin P. This straightforward, even in coincident points we saw that it will be normal to this thing. So omega is minus 10k crossed with 0.75 I minus 1.3 J. So this comes out as, this will be minus I cap minus 7.5 J cap. So this is the absolute velocity of pin P with respect to a coordinate system fixed with the rotating member, this member link RS, this one. Okay, so we've got the velocity. Now the magnitude of angular velocity of link RS. is what is asked. So we've got this. We know that if it has rotation like that, our velocity of this point would have a component like that, which will be nothing but omega rs into 1.6. And we have already got this is nothing but our y component of Vp, velocity of pin P. So velocity of pin P, if we see, we have already got this. Y component is minus 7.5. It is pointing that way. So it is nothing but minus 7.5 by 1.6, which is R of P with respect to, what was that point? R of P with respect to R. R of P with respect to R magnitude is 1.6 meters. It is given, shown here. So that into omega is what will be the actual this thing, omega, actual tangential velocity. This comes to omega rs, which is nothing but minus 4.69 k cap. So it rotates in the clockwise direction, and clockwise is negative because x cross y is out of the plane of the paper, even for this member. So the magnitude of velocity of pin P as perceived by an observer rotating with rs. Okay, so this is the origin, and a person who is rotating with rs, what would be the component of velocity that he will see? We already saw this in coincident points. It will be along the slot. Actually, this is just the slotted member problem posed in a different manner. We have a slider that is passing through this thing. If this member rs had a slot and the pin was passing through that slot, it is one in the same. So we know that our relative velocities are always tangential to our slot, or in this case tangential to our straight member itself. So essentially this is VREL's magnitude. That is the x component of Vp, x component of the absolute velocity of pin P is what the observer would see. So x component is this. So actually VREL, or that person who is rotating with this, would be minus 13 I cap. So the magnitude of VREL is what is asked. It is nothing but 13 meters per second downward, pointing towards R. Okay, the absolute acceleration of pin P is represented by AP, and its x and y components are asked. So first we know here, till this point, till what we have done here, till VREL, we can solve it easily using coincident points. Now if we were to fix the RFR here and observe point P with respect to O, we know that it will have a an acceleration. So let us calculate that absolute acceleration first. So our absolute acceleration of pin P, considering link OQ, acceleration of pin P is acceleration of O plus omega OQ cross R P with respect to O plus alpha OQ cross R P with respect to O. This is 0. It is minus 10k cross minus 10k cross this we found out as 0.75 I minus 1.3 J, and alpha was given to be minus 3.5. So this is minus 3.5 cross, same thing, 0.75 I minus 1.3 J. So this is the absolute acceleration of pin P, because it is connected to the link OQ. So this we can calculate. I component minus 3.5 to minus 1.3. This is my I component. J is J. So let me just add another page here. So acceleration of pin P comes out as minus 79.55 I plus 127.375 J. So this we know that absolute acceleration of point P of pin P is this. Same thing if we were to observe from our rotating frame, that is from our link OQ, we can find out the main purpose of this analysis is to find out the absolute acceleration, angular acceleration and angular quantities of this member RS. We know that the pin is fixed to link OQ and it slides over or inside a slot it moves, howsoever it is, relative to RS. So we have to necessarily analyze it with RFR, a rotating frame of reference, and get the angular quantities here. So how we can get the angular quantities? AP we know, the same AP, if we were to analyze using RFR, now we have got this using link RS. Yeah. So acceleration of P is acceleration of R plus omega RS cross R P with respect to R plus alpha cross P R P with respect to R plus 2 omega Rs cross VREL plus AREL. Okay, so acceleration of R, it is a hinge 0. Omega Rs we found out here, it was minus 4.69 k cap. Alpha Rs we don't know yet. So let us consider alpha Rs to be alpha Rs k cap, the vector to be positive. Let us take it this way itself. VREL we know, we found out that it was minus 13 along it was this component actually. We also calculated it and reported it here, VREL. So what is it that we don't know here now? AREL. But one thing we need to keep in mind is AREL, the entire AREL it is not that the entire thing is unknown. We know some aspects about it. Essentially, I mentioned that this is similar to a problem with a slot. So we can see that when we are rotating with this member, the acceleration relative can only be linear. It is not a curved member. So we essentially know the direction. We just don't know the magnitude. So our ARL, we can consider our ARL to be ARL I, because I is pointing X is along the axis of the member. That is how it will have an acceleration. Positive or negative, that we will see. No, positive and negative, that will come out from mathematics. That's fine. But essentially, identifying the direction is the key here. So let us take it to be positive and then let it come out to be negative, just so that we can be sure about this. All right. So these two are the quantities that we have considered now. And rest of the things are known. So naturally, we have I, J. We can group them, get two equations and solve for these two. That is the key here. So let us do that. Here, add another page here. So we have this. This is AP, which is equal to omega RS we found out to be minus 4.69 K. It is nothing but minus 4.69 K cross. And what is RP with respect to R? The position vector. We know it is nothing but the distance and it is along the x-axis. So RP with respect to R is nothing but 1.6 I because it is just along the x-axis. That is the benefit of aligning our axis with the axis of the member itself so that it just has one component. Make things a little easier. We have 1.6 I plus, let us call this alpha RS cross 1.6 I plus 2 omega cross VREL. VREL we know that it was minus 13 I cap. We calculated it earlier. Plus AREL we know it is I cap. So it is just a matter of grouping them. Let us group the I components first. This will give I. So it will be minus 4.69 squared into 1.6. Sorry, this will have K. Let me take out the vector sign here. So K cross I won't be I. K cross I won't be I. Plus AREL I. This is also I. So I can directly calculate my AREL from here. Comes out as minus 44.355 meters per second squared. So, like Sudhakar had also remarked that it is a negative acceleration. So the direction which we have considered needs to be reversed. So our this is the magnitude. So this is not the magnitude. This is the value we are getting. So ARL, our vector is actually minus 44.35 I cap. Okay. Then we can solve for the next equation 127.375. I'm grouping the J terms now. K cross I is J, so 1.6 alpha RS. K cross I is J. This will be nothing but plus 2 into 4.69 into 13. So my alpha RS comes out to be 127.375 equal to 1.5x, 1.6x plus 2 into 3.39, 3.4 rather, radians per second squared. And this is coming out to be positive, so the direction which we have considered is correct. So alpha RS is 3.4 K cap. So we have found out the angular quantities also. So what was the question here? AP is the absolute acceleration. This we found out. It was minus 79.55 and 127.375. Minus 79.55, 127.375. So the questions are also put in a logical sequence so that it gives the person hints on what is it that next needs to be calculated and how it is to be related. It is just for practice. If anybody does it once or twice, he'll get the hang of it. So alpha RS magnitude comes out to be 3.4 radians per second squared. And magnitude of acceleration of pin P as perceived by an observer rotating with RS. This is again ARL, but we should note that magnitude is asked. So we should report the absolute value. So magnitude of ARL is what is asked. It is 44.35 meters per second squared. So this is how we solve this problem. So if there are any questions, I'm happy to answer them now. Other than this, RFR is only about this. Essentially, we have assembly of articulated rigid bodies. It is one is not truly rigid, so to speak, because it has a slot and something is moving along the slot. So we have to go for rotating frames of reference in order to find the kinematical quantities for that slotted member. The absolute values of that can be found by the other arm which to which it is fixed, and this is how we get the kinematical quantities. So if there are any questions, I'm happy to take them now. Yeah, yes, please. Yeah, yeah. Let me go. Yes, no, because we are rotating with this, right? So we need to account for additional terms also. It doesn't apply for accelerations straight away. Yes, it becomes very immediately we can see just by taking one vector that is in our RFR. If we differentiate it, we see that very quickly it becomes cumbersome. A lot of terms start showing up. So, if you would be taking one component of it along this thing, that will only account for one part of that acceleration. One part of ARL only you will be able to see. So, the actual ARL that would only come out of the RFR analysis. Alpha is equal to 0. Yes. Perhaps, see, it could be rotating in one direction. Let us say alpha omega, it was going clockwise, and then you had alpha applied counterclockwise. So at some point, both countered, it became 0. Alpha was still there, but our omega became 0. So it is quite possible. Unless there are any numerical calculation errors, it is possible. Yeah. Yeah. Yes, it is key. It is key. Yes. Actually, the thing is, if you solve a number of problems, you'll get the hang of it. It looks very formidable, to be very honest. The equations look very formidable. There is alpha, omega, everything is floating around. But essentially, if we come out of that clutter and we see the big picture, what is it that we know? What is it that we don't know? In this problem, if you see, what is it that we know? Absolute velocity of p and absolute acceleration of p, we outright know. That is not at all the question because it is linked to this link OQ carries that pin P. So we know these quantities. We only want to calculate the angular components of the other link for its design anywhere. So that is when our RFR comes in. So the general approach would be you have the absolute velocity, you have the LHS already. RHS, there will be some unknowns which you have to assume, and then grouping I and J components, you'll be easily able to get them. So if you practice somewhat, I think it should be, I think it can be done. It's not that, it looks formidable, but it's not any different than our analysis that we have done. Does that answer your question? I'm not sure what you had asked. I just went on, I digressed a little bit. Yes. Okay. So any other questions? These sheets again, yes, yes, please. And anyway, see, this last week, whatever we discussed, there was a minor error in the acceleration calculation because I'm doing it live, so it is quite possible that some numerical error might creep in. Conceptually, I try my best to be correct. And if there are any numerical errors, I would encourage you that you also point it out if there are. Anyway, I make sure that before posting this on that Google Sheet, I ensure that the calculations are correct. So even in case you find that during the session there was some mistake, it is quite possible that you might find we were getting some other answers there. Appropriately, I will be editing the video also so that there is no confusion at a later stage. But for to avoid this, because I'm also solving it live, it is possible to have some human errors. I'll try to avoid it, but I request you to please bear with me. But other than that, conceptually, I'm not missing out on anything. So that is the key here. Multiplication and evaluation is a matter of practice, so I suppose you people can do it better than I can. So that is what I wanted to remark on just once. Okay, so other than that, if there are any questions, I'm happy to take them now. Okay, so all right. So I would encourage you to practice more. After I'll post this sheet also in a couple of days, so you can just take a look at these questions, try to solve them on your own, and whatever doubts come up, you can ask them in the next session or in the forum also. So other than that, if there are no questions, so I'd like to call it a day, and we'll meet next week for the. So far, we have been dealing with kinematical quantities calculation. Next week, we will be dealing with planar kinetics. So we will bring in force and torque. So essentially, we will be dealing with all that. So let us see. Other than that, if there are no questions, I'd like to call it a day. Thank you. Thank you.